An object of mass 1.5 kilograms is accelerated to 2.2 meters per second squared. What force is required? So it's always good to draw out everything we know about a question. So we've got a block here, and it has a mass of 1.5 kilograms. We know that a force is going to be applied to the block, which is represented by this arrow here. And a force is a vector, which means it's got a size and a direction to it. So the direction of this force is pointing from left to right, or in the positive x direction. And we're trying to find out what the magnitude of this force is. So the size of the force based on the acceleration of this block here. So this vector here represents the acceleration that has a magnitude or a size of 2.2 meters per second squared. And for problems like these, the acceleration and the force point in the same direction. So to answer this question, we need to use Newton's second law. So do you remember what the formula is for Newton's second law? So Newton's second law can be written out like this. So we got force is equal to a constant mass, so a mass that doesn't change over time, multiplied by an acceleration. So for an object of constant mass, its acceleration is directly proportional to the resultant force applied to it. And the acceleration and the force vectors always point in the same direction. So all we need to do to answer this question is plug in the values here. So our resultant force is equal to 1.5 kilograms multiplied by the acceleration 2.2 meters per second squared. And we get an answer of 3.3 newtons to two significant figures. So the second question here, again we're going to use Newton's second law, but it's a bit more complicated. So we have a car with a mass of 1.5 tons, and it's initially traveling at 80 kilometers per hour, which is about 50 miles per hour. So we've got an initial velocity here of 80 kilometers per hour, which is roughly 50 miles per hour. So it's traveling pretty fast. I'm going to write initial state here. I've got the mass is equal to 1.5 times 10 to the 3 kilograms. Now this car is said to be stopped in 11 seconds. So we can imagine after 11 seconds, after braking really hard, that it comes to a stop. So we can say its final velocity is equal to 0 kilometers per hour. Okay, let me tidy this up a bit. So the goal here is to see what force is required to slow this car down from 50 miles per hour to a standstill after 11 seconds. And we're going to use Newton's second law to help us out. So we don't know the force and we don't know what the acceleration is, but we've got the mass at 1.5 tons. But we do have an initial velocity and a final velocity and a time. So the time is equal to 11 seconds. Our initial velocity is 80 kilometers per hour, which we're going to have to convert into meters per second. We'll do that in a second. And our final velocity is 0, which we can just say is 0 meters per second. Now we're going to have to use a formula that is learnt in one-dimensional kinematics. And I've got a couple of videos on one-dimensional kinematics that I'll put up in the card in the corner here. So one of these formulas for one-dimensional kinematics looks like this. So we got the final velocity of an object is equal to its initial velocity plus the constant acceleration on the object multiplied by the time it's undergoing this acceleration. So in our case, our object is decelerating over 11 seconds. 11 seconds is our time. We're trying to find out the acceleration here, or the deceleration, and we've got the final and initial, and we've got the initial and the final velocities here. And for this formula here, this acceleration is constant over time, which means that it doesn't change over time. So we can rearrange this equation here to make the acceleration the subject of this formula, and then we can plug this acceleration into our Newton's second law here to get the force. So let's do that now. So we got the final velocity minus the initial velocity divided by the time, which gives us the acceleration. Before we find out this acceleration though, we need to convert this speed here into meters per second. So I'm going to write out 80 kilometers per hour here, and we multiply this by a conversion factor. So the first step, we're going to convert this kilometers unit into meters. So because we've got kilometers in the top here, in the numerator, we put a kilometers unit at the bottom here, and we put our meters unit in the numerator. So we know that we have 1,000 meters for every 1 kilometer. And because we've got 1 kilometer unit in the denominator and 1 in the numerator up here, these cancel out. So we end up with meters per hour, and this equals 80,000 meters per hour. But we need meters per second. So we have to multiply this again by another conversion factor, where we're trying to convert this hour unit into seconds. So because this hour unit is in the denominator, so at the bottom of the fraction, we need to put an hour unit in the top here, in the numerator, so that they cancel out. So we know that for every 1 hour, we have 300 or 3,600 seconds. So the hours cancel out, and we end up with 80,000 meters divided by 3,600 seconds. And this comes to 22.2 reoccurring meters per second, which we can round down to 22 meters per second to 2 significant figures. And we do this because we only know our initial velocity up to 2 significant figures here. So we know that's 22 meters per second. So now we can work out the acceleration or the deceleration of our vehicle here. So I've got 22.2 reoccurring in my calculator here, and that's what I'm going to use for my initial velocity. So I've got 0 minus 22.2 reoccurring divided by the 11 seconds. And this gives us an acceleration of negative 2.02. And that's reoccurring as well. So this means that if we write this out in full, we get negative 2, 0, 2, 0, 2, 0, 2, and it keeps going like that on the calculator. And that's meters per second squared. But because we only have values to two significant figures, we round this down to 2.0 meters per second squared. So now we can use Newton's second law to find the force required to stop the vehicle. And the force is working in the opposite direction to the direction of motion of the vehicle. And you also notice that the acceleration is negative as well, which means that the acceleration is pointing in the opposite direction to the positive x-axis, or the direction of motion of the vehicle. So the force stopping the vehicle in 11 seconds from 50 miles an hour is equal to the mass of the vehicle multiplied by the acceleration. We get a force minus 3.0 times 10 to the 3 newtons. And the negative sign here means that the force is working against the car's motion. So a force of 5 newtons is applied to an object of mass 3 kilograms. What is the acceleration of the object? So let's draw this out quickly. So we've got a simple block here of 3.0 kilograms, and we're applying a force of 5.0 newtons. And we want to know what the acceleration is of this object. So this is quite a simple problem. And again, all we need is Newton's second law, which is force is equal to a constant mass times the acceleration of the object. To find the acceleration, we rearrange this equation here. So we divide both sides by the mass. The masses on the right-hand side cancel out, and we're left with an acceleration is equal to the force divided by the mass. So our acceleration is equal to 5.0 newtons divided by 3.0 kilograms. And we get an answer of 1.6 reoccurring meters per second squared, which we can round down to 1.7 meters per second squared to two significant figures. So now we have a stone of mass 50 grams, which is accelerated from a catapult to a speed of 8 meters per second from rest over a distance of 30 centimeters. We need to find the average force applied by the rubber of the catapult. So the initial state, our initial velocity, is equal to 0 meters per second. Our final velocity is equal to 8.0 meters per second. So that's the initial state. And our final state is where our stone has reached 8 meters per second at the end of this catapult here. So 8.0 meters per second. And that's over a 30 centimeter distance. So we got the mass of our object, it is equal to 50 grams, which we're going to convert into kilograms in a second. And we've got a distance term here, which I'm going to use the variable s. So 30 centimeters, which we're going to have to convert into meters. So again, like the first question, we're going to need to use one of the equations in one-dimensional kinematics in order to find the acceleration. And we're going to need to use Newton's second law again, which is force is equal to the mass times acceleration. We're not given the acceleration in the question here, but we're given enough information to obtain the acceleration if we use one-dimensional kinematics. So let's first convert the mass into kilograms. So again, we need a conversion factor. So 50 grams is multiplied by some conversion factor. Because we've got grams here, we need grams in the denominator. And we have kilograms at the top here, which is what we're trying to convert it to. We know we've got for 1 kilogram, we've got 1,000 grams. So if we multiply this together, we end up with 0.050 kilograms. And we can do this with the centimeters as well. So we multiply that by a conversion factor. We put centimeters in the denominator, and we're trying to convert it into meters. So for every 1 meter, we have 100 centimeters. So multiply this together, we get 0.30 meters. Now the equation, the one-dimensional kinematic equation that we need to get the acceleration is this equation here. So the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the distance that the object accelerated. And again, for this equation, for one-dimensional kinematic equations, the acceleration is constant over time. It doesn't vary over time. So let me tidy this up again. So we need to rearrange this equation here to make the acceleration the subject of the equation. So if we minus both sides of the equation by the initial velocity, we've got the final velocity squared minus the initial velocity squared is equal to 2 times the acceleration times the distance. Now we can divide both sides of the equation by the 2 and the distance. So divided by 2s is equal to the acceleration. And we can just plug in the values here. So we got 8.0 meters per second squared minus 0, that's our initial velocity, divided by 2 times 0.30 meters, and that'll give us the acceleration. So our acceleration is equal to 8 squared, which is 64, divided by 0.6 meters. And that gives us a value of 106.6 reoccurring meters per second squared. And because our values are only accurate to 2 significant figures here, we have to round this down to 2 significant figures. So our acceleration is equal to 1.1 times 10 to the 2 meters per second squared. Now we can use Newton's second law to find the force exerted by the rubber. So Newton's second law is equal, so the force is equal to mass times acceleration. Our force is pointing in the same direction as the acceleration here. And we're going to get a positive value because we're starting off at rest and we're accelerating up to 8 meters per second. So our mass is 0.050 kilograms multiplied by the acceleration. And I'm going to use the calculator value to get the most accurate value for the force. So 106.6 recurring meters per second squared. And our value for the force is a positive 5.3 reoccurring newtons, or 5.3 newtons to two significant figures.